Good day, everyone, and welcome back to the study group. We are on rings. Definition 6.1. A ring R is a set with two binary operations, addition and dot, satisfying one. R plus is an abelian group, meaning that it is commutative. 2, R is closed on a multiplication, meaning that it's closed on a multiplication. 3, multiplication is associative, and that's the definition there. 4, multiplication distributes over addition, both on the left and on the right. Note, it is not necessary to have an identity for multiply or inverses. You okay? That's important. Note, the first operation is called addition and the second operation is called multiplication. Straightforward. Definition 6.2. Below are some essential definitions. If multiplication is commutative, then R is called a commutative ring. You okay? Notice it is multiplication, not addition. Why is it not addition? Because R plus has to be commutative. That's the first point. Second one, the identity for addition is called the zero of the ring. If R contains an element such that A plus Z equals to Z plus A equals to A, then R is called, then Z is called 0. So that's just the definition of the identity, which you all know. The identity for multiplication is called the unit of the ring. Note, it is not necessary that there exists an identity for multiplication. You all okay? If R contains an element U such that A dot U equal to U dot A equal to A, for all A and R, then A is called a unit element or unity. Same thing what I said, right? Example 3.6. The following are some examples of rings. So Z with plus and dot and Q and R and C. You all understand? Next one. Or. So for the set of complex numbers, what would be the zero of that ring? What element would be the zero element? Zero. Yes? Because 0 is the identity for addition, yes? And what would be the unit for that ring? 1. Because 1 is the identity for multiplication, yes? You all following, right? Nice. Z3. So if we have Z, Z would be -3, -2, -1, 0, 1, 2, 3. So what would Z3 be? Well, we multiply everything by 3, right? What would, everybody's good, right? Nice. So if we're in Z3, what would be the zero of Z3? The zero element. So Z3 is a group, right? I'm telling you all that, right? What is the zero element? What is the zero of the ring? The identity for addition, yes? And in this case, it is 0. What would be the unit of that ring? It would not have a unit, yes? Because 1 is not there. You all see that? and Z2 so for Z2, if we had Z2 now, what would be the 0 for Z2? 0. And what would be unit for Z2? Would have no unit, right? Because 1 by 2 is 2. Great. So exercise 6.4, which we will do now. Let Z be the set of integers and define addition. So addition plus or circle plus and circle dot in Z as follows. A circle plus B equals to A plus B plus 1. So A circle plus B equals to A plus B plus 1, and A circle dot B equals to A plus B plus AB. Question: show that Z circle plus circle dot is a ring. Write down the steps that you would do to show that this is a ring. What would you do? Write it down. Alright y'all, so just these steps, that's all I want. So to prove it's a ring, what's the first thing we need to prove? That Z plus is an abelian group. To prove this, what do we need to show? 5. Y'all know the 5. Y'all should know the 5 by now. If y'all don't know the 5, not an empty. Closure. Associative. Next one. Identity. Last one. Inverse. Plus abelian, right? Yes? Everybody's okay? So I would not go into the nitty-gritty of the proof itself. Again, this is just a general. You all are able to do this. I'm telling you all. All I need, we'll assume it's not empty. We'll assume it's closed, assume it's associative. I need E and I need A inverse. So find those for me. Is you all there as well? Find the identity for multiplication. Using this here, this one, circle dot, right? Use circle dot as well. Find the identity and the inverse. We all got -4 and 6. No, these are just two random numbers I call them. Right, y'all, so for addition, we want the identity, so A circle plus E should be A. Yes? Which means A circle plus B, this is A plus E plus 1 equals to A. A goes off and E equals to -1. Everybody's good? And this is, so what are inverses, right? So inverses now, A circle plus A inverse equals to E, but E is -1. So you get A plus A inverse plus 1 equals to -1. So A inverse is -2 minus A. Everybody's okay? So for dot multiply now, the identity would be A circle dot E equals to A. Again, this is just a rough work and I'm not doing proper statements. Proper statement would be E is the identity if, and then you go on with the equation and then you solve, right? That's the year one stuff. So A plus E plus EA equals to A. Remember, it's this way using here, this one. What you all got? You all got E to be 0, right? This makes no sense. Eh? A equals to minus 1 tells me what? Okay, great. I don't know. We're not trying to solve for A, we're trying to solve for E. I circled it on purpose. We want the identity, so we solve for E. And E is unique, 0 is 0. So 0 doesn't depend on anything. You all follow? Nice. So, with that being said now, so the inverse. A circle dot A inverse equals to E, but E is 0, so A plus A inverse plus A by A inverse equal to 0. What do we want to solve? We want the inverse. We solve for A inverse, which gives A inverse into 1 plus A equals to negative A. So A inverse is A over A plus 1. You got this? Nice. So we're just going a little deeper. For this ring, remember we are in a ring. The 0 of the ring is what? What is the 0 of the ring? Anybody else? The 0 of the ring is what? The 0 of the ring is the identity of addition. And this is my addition and this is my identity for the ring. So the 0 of the ring is minus 1. Yeah? And the unit of the ring is the identity for multiplication, which is 0. You follow? So notice that the 0 is really minus 1 and the unit is really 0. It doesn't make a difference. This example I wrote especially to show you all that. Those are just the names. The identity under addition is called a 0 regardless of what it is, and the identity under multiplication is called the unit of the ring regardless of what the operations are. Yeah? Good. Question 3 there. Does Z have a unit element? And the answer is yes. And the answer is 0. If so, what is it? Let me just add an next part. Which elements have inverses under multiplication? So which elements have inverses under multiplication? Which one? All except for? So we have all So we have all except A is minus 1 or plus 1? Yes? Anybody else? Half the marks. 4.
Whoa. Rewind.
Call an element that has, okay, so if I say 5, right? What is the inverse of 5? Somebody? 5. Call it out, look at there at the bottom. Minus 5 over which is, why is this? It is correct, but it is also not relevant because it is not in Z. It is not in the set. So, which elements will have inverses? Figure that out now. Zero, maybe, you tell me. Write it down and see if when you put 0 as A, if you get an answer that's in Z. Yeah, what's the answer again? See, well done. Any other? I feel you're looking at it not completely. Our goal is for this to be in Z, yes? Is 8 in Z? Yeah? Is 8 over 1 in Z? Yes? Is 8 over minus 1 in Z? So, a requirement for this to be in Z is that the denominator must be plus or minus 1. So take that equation and solve for 8. Because if it's anything else other than plus or minus 1, you get a fraction. You understand, right? This is really year 1 material, but just to fully exhaust. Because you all did this in year 1, I'm sure, because I remember doing it with you all. Right? The exact question. So A plus 1 equals to plus or minus 1, which implies A plus 1 equals to 1, A plus 1 equals to minus 1. You follow? And if you sub those two in that, you will get values that are that are in Z. Nice. Good. Definition 6.1. Anybody has any questions before we move on? So you all understand a ring now, right? Good. A subring of a ring R is a subset which is a ring under the same operations, addition and multiplication. So more or less the same thing like a group. You have a group G and you have a subgroup of it. It's just a subset of G in which the operation is the same. Yes? The following are some examples of subrings. So Z is a subring of Q. So So the set of integers is a subring of the set of rational numbers. Q is a subring of C singleton 0 and R are subrings of R. Everybody's okay? Singleton 0 is the set that has 0 only.
So you can have R as a subring of R.
Yeah? Just like I can have G as a subgroup of G. Or 5 is less than or equal to 5. Yeah? (49) Let definition 6.7, let R be a ring. A subring S of R is called a proper subring if and only if S is a proper subset of R. More or less straightforward. Next page. Proposition 6.8. Let S be a non-empty subset of a ring R. Then S is a subring of R if and only if for any A and B in S, A plus B is an S and AB is an S and minus A is an S. I have proof, I have self-study, but let's just go through it. Right? So one more time. Let S be a non-empty subset of R. So we have a ring and we just have a non-empty subset. That's all we know. S. So S is a subset. S is a subset of R if and only if. So we need to show that S with plus is a group, an abelian group, yes? So we take two elements in S, A and B. You'll remember the formula to show subgroup A, B inverse. Nice. So that's what we do there. So we take two elements. So the first thing, we have A plus B is an S, which is closure. The second one, straight down to the right, minus A is an S. So if minus A is an S, then that means inverses exist in S. So we could combine the minus A and S with the A plus B to get the A minus B and S, which is what we normally use. Normally it's A, B inverse in the group, sorry, in the set, but because it's addition is the operation, it's A minus B, right? So A plus minus B. And AB is an S, that is the product, which means the closure for multiplication in S. So we take commutativity with respect to addition and associativity from the ring itself, because it is a ring and the operations are the same, which means it would be commutative and it would be associative. You are following? Nice. That's more or less what the proof says. Conversely, if S is closed under addition, taking the relevant inverses, then S plus is a subgroup of R plus from group theory. That's what we did before. S is closed under multiplication, associativity and distributivity. Oh, I forgot about distributivity, right? So that was the last point, and that holds because R is a ring, and being a ring, multiplication distributes over addition, and it's a subring with the same operations, so it will be distributive as well. Nice. We have, yeah? Definition 6.9. An element A which is not equal to the 0 of the ring. So when we see A and when we see 0, it's not 0, it's the 0 of the ring. So in this case, the 0 of the ring was minus 1. Yeah? This is a very important definition. So an element A that is not the 0 of the ring is called a zero divisor if there exists another non-zero element B in the ring such that A and B are not equal to 0. So the product of A and B, the product of A and B is equal to 0.
Which 0 is that? The 0 of
The 0 of the ring. So in other words, in definitions it will always be the 0 of the ring. Because these definitions, you have no group, you have no binary operation, you have no function, so we don't know. Elements are not necessarily numbers. These elements could have been cosets. You follow? Or it could have been boy, girl, rabbit, animal. Yeah? So we can't talk about boys and talk about zero. Where's zero come from, you know? So there's this little, I don't know if this is a joke, but you know, you have this group and then I don't know how to put it, boy. Just hold on. Right. So let me say you go by grandmama and your lineman, right? And everything good and cool and nice. And you're doing some wickedness. And your mom come and you know she could be vexed with you, right? She could get everybody tense up, right? So she could like people in problems. But then you know if your grandfather come, you can neutralize your mom like hey, leave the child alone, you know. So that's like the element and the inverse. That's okay, you all don't have to share the enthusiasm. Zero divisors. I have a handout on this that is upstairs. So I'll just briefly go through. So in R does not have any zero divisors, which is great. Which is the best thing in the whole world. The fact that R does not have any zero divisors means we can have A and B equals to 0, and that could mean A equal to 0 or B equal to 0. You all follow? But if we were in matrices, say, let's just say we have this matrix A and this matrix B, and we get A by B to be 0, meaning the zero matrix, we cannot say that A equals to 0 or B equal to 0. You all follow? This is what zero divisors are. So that's why we cannot do this in matrices, because there exist zero divisors. In this case, A and B are zero divisors. You all follow? I have a handout printed. I'll bring it tomorrow. So thank you all for coming to study group today. We will see you all tomorrow, in which we will go through, we'll conclude with rings.
Yeah.
We will tell the story of groups. We will make analogies between groups and rings, and tie up any random questions you all may have. So with that in mind, we are on rings. So we covered the basics of rings yesterday. We are on proposition 6.8 rings. Proposition 6.8. Let S be a non-empty subset of a ring R. Then S is a subring of R if and only if for any A and B and S, we have A plus B and S, A, B and S, and minus A and S. So proof, we went through this yesterday. So I wouldn't go into the proof now, but I want to draw your attention to the other proof, the other theorem, which is on the handout. So let's look at that. A subset S of a ring R is a subring if and only if, so it's biconditional. S is non-empty, makes sense. The second one, S is closed under addition. So if A and B are in S, then A minus B in S. You all understand what this one gives, right? This one shows that S is a group under addition. And the last point, S is closed under multiplication, and if if A, B, and S, then A, B, and S. Definition 6.9. This is an important definition, very important, so please pay attention. An element A which is not equal to 0, the zero element of the ring. You all remember what the zero element of the ring is? What is the zero element of the ring? Well done. Identity and addition. Yes. I'm smiling. Of a ring is called a zero divisor if there exists another non-zero element of the ring called B that is in the ring such that AB equals to 0. You understand that? So in other words, zero divisors are bad, okay? In our case, it's bad. So I'll explain why. So on the handout, we have AB equals to 0 implies either A equal to 0 or B equal to 0. Sorry, does not imply that. So matrices, contains zero divisors. So in other words, if we have that equation a b equals to 0 bar, then we cannot say that either a equal to 0 or b equal to 0. You follow? Nice. Which means, however, if we were in our normal field R, if I have x minus a into x minus b equals to 0, I could say that x equals to a or x equals to b. And this is because R does not have any zero divisors. You follow? Yeah? Nice. And that is the big point. Lovely. 6.2. Ring homomorphism. A mapping phi from R plus dot into R prime circle plus circle dot is said to be a ring homomorphism from R into R prime if and only if. So just as we had group homomorphisms, now we have ring homomorphisms.
Okay.
4 groups we had 1 operation, 4 rings we have 2 operations. So it makes sense that the homomorphism satisfies both. So the first point is that the image, look how we read it, the image of a sum is the sum of the images. You all see that? Let me just draw that on the board. So the image of a sum is the sum of the images. So the image of this sum is the sum of the images. Yes?
Yeah.
Good. The second one is the product of the images, sorry, the image of the product is the product of the images. And this has to happen for all A and B in the domain. Yes?
Circle addition has certain rings.
No, because we have 2 rings, remember we go from 1 ring to the next ring. So to differentiate the addition in this ring and the multiplication in this ring from this, we use different symbols. Yeah, so it didn't matter what we use there, it just has to be different. Unless if the operation is the same. Yes? So, just as we have group homomorphism and we have group isomorphism, we have ring homomorphism, and guess what we have now? Ring isomorphism. So who could guess what a ring isomorphism is? A homomorphism that is 1 to 1 and 1 to 2. Yes? Straightforward. You all follow the analogies going, right? So once we did the most of the work in the groups, well, we still have a lot of work to do in rings, which we will not do. But it's just to give you all some analogies so you could have some structure into where the course goes. Question. Look at this lovely question. Let R plus circle multiply be a ring, and let R plus dot. So R plus dot is normal plus and normal multiply. We define addition and multiplication in the ring as follows. So this is how I define it there. Show that both rings are isomorphic. So in other words, it's a homomorphism and it is bijective. Next time, proof. We define a homomorphism so that I gave you all the homomorphism. Because it would kind of be hard to figure it out. Little hard. Look at, could somebody read the next line? So take 2 minutes and please attempt it now. No, you could work in groups. Huh? I mean, this is group theory, right? I just love these jokes. Yes. So what you all could do, instead of trying to work from one side and go to the next side, take the left hand side, work it out, simplify, then take the right hand side, work it out, simplify, and then show that they're equal. You all follow? Nice. I hope you all appreciate by now the fact that SG is the left coset. I understand that. By the end of the class, you would know that RA is the right ideal. And I use RA because you could put J. My name is Rajesh, okay? Alright, so let's attempt this question. So we know that phi goes from this set into this set. Yes? And we define phi by phi of an element is a plus 1. So phi of a equals to a plus 1. Yes? Great. What we need to show for homomorphism is phi of a sum, but we are going from this set to this set. So the addition in this set is circle plus, yes? So we need to show that phi of a plus b, so a circle plus b equals to phi of a. The operation in this set is normal addition plus phi of b. Everybody's okay? The second point that we need to show is that phi of a product, which is a circle dot b, equals to phi of a normal to multiply phi of b. So this is the setup. So what I would suggest is, normally we would start from one side and go to the next side. The math might be a bit tricky as you all are now doing it. So what to do? Proof, let a and b be elements of this set. Now phi of a circle plus b equals to, work out simplify, and then take this side, work out simplify, and then show both sides are equal. You all follow? So let x and y be elements of R. Now phi of x circle plus y. Now phi of x circle plus y equals to phi of x circle plus y is, in the notes, it's defined, x circle plus y is x plus y plus 1, yes? And phi of this is what? X plus 1 plus 1 plus 1, right? Remember, this is how we define it. Phi of anything is the anything plus 1. So in this case, phi of this is this, and we just plus 1. Yes? And well, because I have sight, you can realize you can replace this as phi of x plus 1 plus y plus 1. You all see it? And this here, x plus 1, is what? Phi of x. So this is equal to phi of x plus phi of y. You all okay? So an important point to note is we need to pay attention to the specific binary operation in each ring. Which one is first and which one is second. Nice. Right, so I will give you all a few minutes. Attempt the multiplication one, yes? Anybody got it all by the way? Yeah. First part? Good. And again, the good thing about this is just an introduction, right? Just to find out, hey, you know, this is cool. So if you're having problems, take the left hand side, expand, simplify, the right hand side, expand, simplify, and then show that they're equal. Because it might be difficult to factorize one side into the next side if you're not seeing it. Right, so we have additionally phi of x dot y equals to, and this gives phi of x plus y plus xy, which is x plus y plus xy plus 1, because that's how we define phi. And so phi of x dot phi of y equals the phi of x is x plus 1, sorry, it's not, it's here. And phi of y is y plus 1. We expand, we get xy plus x plus y plus 1, which is, we just make it look the same, which is x plus y plus xy plus 1, which is, and we need to write this phi of x circle multiply y. And we conclude, hence, phi is a homomorphism. Yes? It takes a while because you have so many functions you're dealing with, and then you have this homomorphism and that homomorphism. You have this function and it moves from this element, sorry, this ring to the next ring. So we need to show one-to-one and we need to show onto. So one-to-one should be straightforward. So let xy be in R. Assume that phi of x equals the phi of y, and we want to show that x equals to y, yes? Phi of x is x plus 1, phi of y is 1 plus 1, x plus 1, which implies x equal to y, straightforward. Hence, phi is one-to-one injective. I'll give you all a minute or two to go through the onto, right? We take an element in the codomain, yes? So the codomain is still R. So that so for onto, we take an element in the codomain, which is R. So let y, well, R, let's just say R, be in R. Then R minus 1 will be in R. And phi of R minus 1 is R minus 1 plus 1, which is R. Does that follow? Hence, for all R in the codomain, there exists an R minus 1 in the domain such that phi of R minus 1 equals to R. Hence, phi is onto. Yes? Therefore, the result follows. Homomorphism one-to-one onto. Therefore, the result also there. Therefore, yes? Nice. Alright, nice. So now we're on ideals. So section 6.3, ideals and ring homomorphism. So there should just be ideals. So now we're on definition 6.12. A subring I of a ring R is an ideal if whenever R is in R, so any element in the ring, and A is in I, so you have any element in the ideal, then the product A by R or R by A is in the ideal. So in other words, if we have a ring, if we have a ring and we have an ideal I, and you have an element R in R and an A in the ideal, then if they meet, so if they meet up, he get pulled in, get sucked in like a black hole. You follow? So let's just say if you have humans, and humans could live where? In the light. Oh yeah, and in the dark. But then it have vampires. And vampires can live where? In the dark. And a human meets a vampire and they turn. So then the human touches the vampire, which is the ideal, and they turn to a vampire. So now they can only live in the dark. You'll love it, huh? Yes. But you understand, right? So just remember, once you interact with the ideal, once you enter the ideal, once you interact with the ideal, you cannot leave. You are there, that's it. You've been sucked in. Yes? Nice. Note, if R is commutative, remember R is commutative if multiplication is commutative, right? Because a ring addition has to be commutative. We only need to worry about multiplication on one side. Moreover, generally we can speak of left ideals and right ideals and two-sided ideals. So same thing with inverses and identity. Left inverse, right inverse if it has, then it's the inverse. Right identity, left inverse has the identity. Right ideal, left ideal has both the ideal. You all follow? Yeah. Theorem 6.14, a non-empty subset. So now this is important. So this is a subset, not a subring. Yes? So a non-empty subset I in a ring, so now we have a ring and we have a subset I in the ring is called an ideal if and only if it suffices that one, for all A, B, and I, then A minus B is an I, which means what? I is a group. You remember the group? If A and B and I, then A. If A and B and H, then A, B, and inverse in H. In this case, H is I. So get high. In this case, the operation is minus. So instead of A, B inverse, it's A minus B or A plus minus B. And it's in I, yes? So that gives you the fact that I is a group. And then the second one gives you if R is an R and A is an I, then the product. So that satisfies the ideal property from above. You all okay? So the proof, we won't go into the proof. Example 6.15, the following are examples of ideal. I'll just go with one of these. So nz equals to kn where k is in z. For any n in z is an ideal in z. If n is 0, so this would be the example. If n is 0, we get a 0 ideal, an ideal of any ring. So in other words, you have 0 by k, k by 0 is 0, 15 by 0 is 0, so everything is just 0. So you get sucked into 0. You understand? Nice. If n is plus or minus 1, we get z, which is the whole ring. So that's more or less straightforward. 1 and it's minus 1, you get the whole because it's still on z. So we turn the page, and we have 3 more examples which I will leave for you all to go through on your own time, which hopefully will be before semester starts, because just assume we have class on Monday. Take Monday and review everything. That's all. 6.4, some definitions to end with. Yes, we are nearing the end. Definition 6.16. A field is a commutative ring, meaning multiplication is commutative, in which the non-zero elements, so non-zero elements, in that we remove 0, forms a group under multiplication. That is a field. Or, a next way of saying that is a field is a commutative division ring. The definition of a division ring is below. Some examples of fields are Q, R, and C. You follow that? So that's why C is the set of complex numbers. We don't say the set of complex numbers, except for secondary school. The field of complex numbers, the field of real numbers, the field of Q. You all follow? So it's a difference, it's a big difference. Anybody knows why Z is not a field? Why is Z not a field? Let's read back the definition. Because multiplicative inverses do not exist. So the inverse of 2 is a half is not in Z. So it's not a group under multiplication, yes? Lovely. Definition 6.17. A division ring is a ring in which the non-zero elements forms a group under multiplication. So the difference between a division ring and a field is just commutativity. You all follow? That's why the second definition of a field, well, not the second definition, but alternative way of saying it is a field is a commutative division ring. And it makes sense, right? Because division ring, you would want to divide. But if you have 0, then you can't divide because you can't divide by 0. That's why we remove all these 0 elements. Well, the 0 of the ring. Definition 6.18. A ring is called an integral domain if the first thing is R is commutative, meaning that multiplication is commutative. And the second point is R has no 0 divisors. Remember 0 divisors, what we did just now? A, B equal to 0, then A must not be equal to 0 and B must not equal to 0. So if a ring has 0 divisors, then if A, B equal to 0, then that could be solved where A could not be 0 and B could not be 0. But if it has no 0 divisor, then that means that A must be 0 or B must be 0. Do you follow? Or did I just confuse you all? I think you're all good. The third point, R has an identity under multiplication written as 1 that has 2 asterisks, and the last point, 0 is not equal to 1. So when we say 0 is not equal to 1, I mean the 0 of the ring is not equal to the unit of the ring, meaning that the identity under multiplication is not there in the addition. And that is because of the note at the bottom there. If 0 equals to 1, then x by 1 is x, and so x equals to x by 1, but if 1 is 0, then you get 0. So you get 0 equal to 1, which means that the ring is the 0 element. Definition 6.21. A Euclidean domain, here look at it, D comma plus dot and D. So now we have 2 binary operations plus D. Consists of an integral domain, which is what we did above, together with a D function, such that these 3 properties hold. And I think it's a nice way to end this study group session, yes? Because I mean, you all hear, you know, the Cartesian plane, Euclidean domain, Euclidean space, integral. You all never heard those terms before? That's okay, you'll hear them soon enough. But it's good to know at least. So that is the definition there. We have those 3 points. And this is as far as I would like to take you all for this study group session. So what I want to do now is actually conclude summarizing where we came from, the importance, straight up until now, make some analogies with rings and groups, and then we'll conclude today. Anybody can think of any motivation why we want to study group theory though? Marx. Why would we study group theory, or why they created group theory in the first place? Analyze numbers. Yes. Okay, so what happened was a long time ago, mathematicians realized that in seemingly disjoint areas of mathematics, certain items or properties were shared among different areas. So, for example, in these are the real numbers. We had the identity, so we had a plus 0 equals to a. That's a set of real numbers. Everybody knows that. And then when we went into matrices, we know we had a, b, c, d plus 1, 0, 0, 1 gives you back a, b, c, d. And then if you go into permutation, so permutations exhibit properties like this as well. And when you do the linear differential, homogeneous linear differential equation, the solution space has properties as well. And so the mathematicians realize that wait, if we have seemingly different and disjoint areas of mathematics that all share these common properties amongst their elements, then maybe there might be something more. So then they examine and they realize, wait, we could call a structure, we could form a structure called a group that has these properties. And we realize if we analyze a group and we formalize what a group is, well, they call it a group, and we know, then if we have an example of a group which could be R, or example of a group which would be the matrices, or example of a group which would be the linear homogeneous solutions, then once we know the properties that hold for the group, it will hold for those specific cases. You follow? So that's why it was created. And it works really nicely because it saves you a whole set of work, meaning that you don't have to prove it for matrices and then go and prove it for a set of real numbers and then go and prove it for linear differential equations and then go and prove it for permutations. So you just prove it, you prove it as a group, you prove properties of the groups. That's why most of the proofs, in fact all of the proofs are abstract proofs. If this was an element and then you multiply one by the left hand side, multiply one by the right hand side, because you really don't know what they are, because they could have applications in so many different fields. You follow? So that was the motivation why we started groups, why groups came about in a very short manner. The fathers, I wouldn't say the fathers, but the main people you need to know about in group theory are Galois. So his name must pop up. Someone called Abel, and who could guess the last one? No, his name is in the course. His name is in the course. Lagrange. Yes? I should bring that up tomorrow. You know. So you follow? So Galois is spelled like this, right? Not W-A, right? It's spelled like this. Abel and Lagrange. You all know Lagrange. Great. So arriving naturally from a group, we have properties. So just as you have with anything, if you have a parent, you can analyze characteristics of the child. You have a group, you analyze subgroups. So first we had a group G, and we realized we had subgroups H. Yes? And which means that if we know properties of a group, then the subgroup will have those same properties because it's a subgroup of the group. Then we met Lagrange theorem. Lagrange theorem is a huge theorem, one of the biggest theorems at this level. It's huge. What Lagrange theorem says in a different way is, if there is a subgroup of a group G, then that means that this subgroup partitions it, G. You follow? It gives a restriction. So if I have a group G, then I have a group G. I'm not so sure if I can get partitions of G. You follow? But if I know G has a subgroup H, then I'm sure I can get partitions of G. Because remember we defined the mod H. The mod H equivalence relation. And the cosets partition G. So we have a group, we have a subgroup G. Sorry, we have a group G, we have a subgroup H. From H we can form cosets, which would be H by A or A by H. Everybody's okay? These partition G. Then we met Lagrange's theorem, which says that the order of G divides the order of H, which is great. So in other words, if I have a group of order 10, then possible subgroups would be of order as well. Yes? But does this guarantee that I will have a subgroup of order 1, 2, 5, or 10? No, the converse is not true. It just says that if there's a subgroup, then the subgroup must have order that is divisible, that divides G. Everybody's okay? Now, if you go high up in group theory, so a second course in algebra, we try to push the converse of this theorem as much as possible. So in other words, we try to get conditions on G that would ensure that there is a group, say, of order, of some order, a subgroup. You all follow what's going on? But that's not now. That is a bit later on. And so that's where we go into P groups and group actions. But this is generally in an undergrad elective course, not in a core course, right? So if you choose Algebra 2, then you know you're going to have a lovely time. Really, really great time. So then, we moved on from there. So we have Lagrange theorem, we have cosets. We realize that, wait, if we have HG equals to GH, then what could we say? That H is normal in G, yes? So now we introduce normal sets. So H is normal in G. And if H is normal in G, then we can form the factor group. So we form the factor group, or the quotient group, which is G on H. And the elements of G on H would be cosets. So it will be H by an element in G, yes? Everybody's okay? Using this now, we introduce homomorphism, which is just a special mapping which the sum of the product is the product of the sum. Sorry, the image of the sum is the sum of the images. So we introduced homomorphisms, and we came up with the first isomorphism theorem, which is huge, or the homomorphism theorem, which says that if we have a homomorphism from G to G bar, so G bar is the range of G. G is not necessarily G, G could be H. So we could G could be 1, 2, 3, and H could be A, B, C, D. But if 1 maps onto A, 2 maps onto B, and 3 maps onto C, then this G bar will just be A, B, C, the range. You all follow? Nice. So if we have a homomorphism from G to G bar, where G bar is the image of G under phi, then G, the quotient group G on the kernel of phi is isomorphic to the range. Everybody's okay? Why is this important? This is important because we can get properties of big groups by analyzing smaller groups. So if G, let's just say if G had 1,000 elements, I'll use the same example, and we were to somehow, if we wanted to analyze properties of these groups, this would be 1,000 elements, right? We have to do analyze each element and determine different things. However, if we realize that, wait, we have a subgroup H, and the order of H is 500, yes? Let's assume H is a normal subgroup, right? Then, what would be my cosets? HA would be my coset, yes? And how many elements would HA have? 500 elements HA would have. Remember HA is a coset, right? So the coset would have 500 elements. And remember cosets form an equivalence relation, right? For cosets partition the set. Which means that it's either equal, if there's a common element between two cosets, then both cosets are equal, or they're different, they're distinct. So if I know each coset has 500 elements, how many different cosets will there be? 2, yes? So which means I can get 2 cosets. So in other words, I would be able to get so this will be mapped onto something with just 2 elements. I'm just saying A and B. So in other words, by analyzing this smaller set, I can get properties of my bigger set. Of my bigger set G. You follow? Remember, G over this is a smaller set with 2 elements, and this is isomorphic to the range, but this is also isomorphic to this, yeah? So in other words, you have an element with 1,000 elements, you have a group with 1,000 elements, you form the factor group, you realize, hey, we have 2 elements in the factor group, you analyze those 2 elements, which means the properties that are common to both those 2 cosets would be common to the group. You all following? So it makes life much easier when dealing with large groups. Nice. From there now, so from there we introduce another binary operation, we call it multiply, and we get something called a ring. So we have a ring now. From rings, we have an ideal as well. And the ideal would act as the normal subgroup. So the ideal in a ring acts as a normal subgroup in a ring. So so then, which we did not do, we could have a quotient ring. And this will be analogous to, guess what? The quotient group, right? Yes. What's that? No. Yeah. Yeah, so the ideal in a ring is analogous to a normal subgroup in a group. You follow? But we didn't. Yeah, right? So the quotient ring in rings is analogous to the quotient group in groups. You follow? Then we have homomorphism / isomorphism. Analogous, same thing more or less in groups and rings, yes? The only difference is in rings you have a second operation to deal with. Yeah? And then we just go on from there. So there would be respective isomorphism theorem for rings as well, and you go down and you go down and you go down and you go down. But that's not where we're going, right? So my goal for this whole mini study group session is to make learning of the course easier. Not so that you come to this and you feel that you know everything when the semester comes and you don't need to go to class. Trust me, you will need to go to class. This is simply to say when you reach in class on the first 2 weeks, you understand what's going on, you have an idea, but we have left out an enormous amount of work. There are a lot of proofs we did not do, things like that. You need to go so that when you encounter those proofs in class, you would know, or you would be able to follow what's going on. You understand what's going on? Nice. Great. I think that is it. Anybody has any questions? So I'd like to thank you all for coming to today.